So today we're talking, and I'm emphasizing all day, it's this gas phase spectroscopy, because we won't see those rotational levels if we're not in the gas phase. In the liquid phase, they'll try to rotate, but instead of rotation, they just kind of wiggle a little bit, so the electric field comes through, and there's a molecule in the liquid state. It can't rotate all the way around, but it can kind of oscillate a little bit with that light, but there's no quantized effects. You don't get any absorption. You just get sort of a broadening of the vibrational peaks in the liquid state. But that motion where it's not quite rotation, this really isn't a word you need to remember, but there's a word for it. It's called libration. Okay, so it's just a trivia. Okay, but so libration, where the molecule tries to rotate, but it doesn't, and it kind of bangs into the molecules around it. That's called libration. And so it's like vibration, but spelled with an L. So who knew? Okay. Yeah, so that's and those kinds of motions that really have molecules banging into other molecules, that's really the source of the speed of sound in a substance. And so that's really creates shock waves in the substance and so on. So you can use that light to create physical effects in the material as a whole, but you don't really see the molecular effects. So now we're talking about rovibrational energy levels. So this is rotation and vibration on top of each other. Last time was pure rotation. So we were down here in the bottom of the figure. So at the bottom here, this would be pure rotation, and that would be the microwave region. But today we're going to be talking about the combination of these two. So we're going to have a fundamental vibrational transition with rotational changes on top. And so that's in the infrared because we're in the vibrational transition. That makes it into the infrared, but then we'll also have on either side of that vibration the rotational effects. And we'll see peaks, a lot of rotational peaks on top of a vibrational peak. And so here are the energy levels. We've zoomed in on that yellow box, and now we just have the V equals 1 state at the top. You see that over here, V equals 1, and V equals 0. Let me just make sure we're getting this recorded. Okay, 1 second. Yes, we're good. Okay, so we have V equals 1, the upper vibrational state, the lower vibrational state, and then we have J and J prime. J double prime, again, the V double prime and J double prime, those double primes are the lower states, and the primes are the upper states. So that's something that you need to sort of put into your memory for this lecture, and then for next week's lab, and then the iodine lab. You really need to focus on the double prime states being the lower states, and the single prime states being the upper states. So J double prime are all of those lower vibrational rotational levels. So the rotational levels on top of the lower vibrational state, and then the J primes are the upper rotational levels. So this is a molecule that's excited vibrationally and rotating. And both motions are quantized. So there's quantum numbers associated with all of these different things. And then these are the different transitions that are allowed in the infrared. We can have no change in the rotational state. So if you follow this line across, you see that that's quantum number 4. So J double prime is equal to 4 for that one. And you come up here, and it's also J double prime, or J prime equals 4. So delta J was 0 for that one. But delta V was not 0. Delta V was 1. It went from 0 to 1 in the vibrational quantum number, but delta J was 0. So the Q branch lines are all delta J equals 0. So you can bracket that or do what you want right here. So this is delta J equals 0. And that's what defines the Q branch. No change in rotational quantum number. So these are the energy levels up top. Let's look at the spectral lines down here at the bottom. And so those Q branch lines would show up all clustered together, and their intensities would join together. So there'd be a really tall peak right at the vibrational frequency. And so that is where the vibrational frequency is, the pure difference between the vibrational levels, because there's no difference in J. So it's from V equals 0 to V equals 1. And so that Q branch is telling you right where the vibrational difference is. Let's look over here. This would be the P branch. And down at the bottom, you have J equals 1, and up here, J equals 0. And over here, let's look at this one where we can really see the differences. So this is, the lower state is 8. So I'll draw an 8 there so that you can see it clearly. And up here is 7. So this is delta J equals -1. And those are at lower frequency values because J went down. So those are shorter arrows, right? If they're shorter arrows, they're lower frequency. And so that would be what we call the P branch. And you'll see in increasing wave number, it goes PQR. So it's the alphabet. So the lower ones are P, the middle ones are Q, and the higher frequency ones are R. So as it is in alphabetical order, that's the same order for frequency. So this peak down here would be the 7 to 8 transition. And so we would label that one P7. And so you label them with the branch label, P, Q, or R, and the lower J value. And so that's the P7 line, which tells you it's going from 7. I'm sorry, did I screw that up? Back it up. Okay, so let's go back down here. Let's find my little eraser. Okay, you get your eraser. Okay, we're going to erase that. Okay. All right, so let's go back to the pen. All right, so this is the P branch. We label it with the lower J value. And so this is the P8 line. And it went from 8 down to 7 because it's a P branch line. Okay.
So if it was emission, would it go down and you would still label it with the 7? Do you label it with, like, do you do initial value that you label with, or
you would do it with the lower state?
Still?
Yeah, still. So it'd be an emission line, but it would be the P8 emission line. Yeah. That way it's no confusion. It's always P and then the J double prime value. And just by saying that it's emission would tell you that it started at 7 and went to 8. Okay. Yes. Because that would be where it would show up in the spectrum. And then now let's look at the R branch side. So the R branch is going up in quantum number. So let's look at this last one here. This is level number 6. And up here is level number 7. And so these are delta J equals +1. And so this last one here, we would label R with the lower value 6. And because it's an R, we know it's going 6 to 7. It's going up. And over on the left, we had the P8 line. Because it's a P, we know it's going down. So it's 8 down to 7. So whatever that subscript is, that's the lower J value. And then you use whether it's R or P to tell you what the upper state is. Okay. And so these are the spectral lines that we would see. Now there's one thing to note about the Q branch. Remember, light has 1 unit of angular momentum. And that angular momentum describes the P and R branches really well. So if it's an R branch, light's angular momentum was going with the molecule and it bumped it up 1 unit of angular momentum. So it jumped up a J value when it went absorbed. As far as the P branch, light's angular momentum was going in the opposite direction of the rotating molecule. And so it took a unit of angular momentum away. And so it went from P8 down to P7. It still absorbed the light vibrationally, but rotationally it went down by 1 quantum number. But what's weird about the Q branch is what happened to the angular momentum of light? Angular momentum is conserved. That's one principle in physics that applies in automobile crashes and quantum mechanics, is the conservation of momentum. So that's a nice stable law that you can follow all the way down to the atomic level, is the conservation of momentum. So if light has a unit of angular momentum, how can there be a Q branch? Because there was no change in J value. And the answer is it has to have some sort of angular momentum in the vibration for that to occur. So here's a spectrum of CO2. There's water in there too, but let's focus on the two branches for CO2. The two bands, the spectral bands, where it's just a sort of an envelope or it's a vibrational absorption in the gas phase, but because there's so many rotational lines as well, they just take this whole region and call it a spectral band. So it's a band of spectral lines. Okay? And the parallel band, shown up here, this one here, the parallel band, that parallel means that the vibration is parallel to the z-axis. Okay? And that, if my head's the carbon and my hands are the oxygens, this is the asymmetric stretch. And there's no angular momentum associated with that stretch. But this one over here on the other side, on the right side, the perpendicular band, that stretch is perpendicular to the z-axis. And so again, head is the carbon, my hands are the oxygens, and it's not this motion parallel to the z-axis, it's this motion, okay, perpendicular to the z-axis. Well, how does that motion have any angular momentum? Well, by itself it doesn't. But notice that, say this is the x-axis and this is the y-axis, and that's a degenerate mode. It can do this. It can do x, y, minus x, minus y. And so the perpendicular band, that's doubly degenerate, has angular momentum in it. Do you see how it's a rotation now? The rotation that previously was not defined around the z-axis, now because of vibration, actually has some rotational character to it. And it can absorb angular momentum. It can go faster this way if it's vibrationally excited. And that can give us a Q branch. So perpendicular bands can have a Q branch. And that's what we see here. You see that dip. Now this is a single beam spectrum, so we're looking at the source, and then we're missing some light wherever a molecule absorbs. And so this is, all the peaks are down. So this region right here is the CO2 bend, and we see that Q branch. And that angular momentum of light is being absorbed in the vibrational motion, not in the rotational motion. So you can get a Q branch. Even though there's no change in J value, the angular momentum went into the vibration. Okay. This is also a useful tool in spectroscopy, because if we were somewhat confused as to which one of these was the perpendicular band and which one was the parallel band, we would know right away by seeing the Q branch which one was which. So this is a nice tool for small molecules. We can say, okay, this one is definitely a perpendicular band because it has a Q branch, and that helps us assign those vibrational modes. That's getting, kind of down into the weeds of molecular spectroscopy, but that's where we get the Q branches. It's whenever the vibration can absorb some of the angular momentum of light, then we don't have to put those changes in the J values. They can just be in the V quantum numbers. So then let's talk about the different energy equations. So here's the transition. Here's the energy equation. We have the vibrational energy here, V plus a half times hc nu. Again, the nu is the vibrational frequency, and if it's in wave numbers and you want to talk about energy in wave numbers, you don't need the hc. The hc is only there to convert it to joules if you wanted to work in joules. So you can throw h and c in there to convert your units. That's totally fine. Just use them as unit conversions. And you do that a lot of times when you're trying to get the units to work out. Oh, I need, what do you do if you need something per mole? Well, you throw Avogadro's number in there. What if you have joules per mole and you want to just get to joules? Well, you take Avogadro's number out and divide by it. Okay, so get used to using these fundamental constants as unit conversions. So that's what the hc part is for the hc nu. And the same over here, hcb. B is in wave numbers. It's the rotational constant. J is the quantum number. And again, if you wanted to talk about energy in joules, you would put the hc conversion in there and get out of wave numbers and into joules. If you want to stay in wave numbers, just get rid of those hc's. Okay. And now this is neglecting anharmonicity and a thing called centrifugal distortion. Just think about that word. What do you think that means? Centrifuge, right? As a molecule spins faster and faster, it distorts the structure. And what it's going to do is it's going to stretch the bonds. So the atoms get farther and farther apart the faster they spin. Okay. And so we're neglecting that in this energy equation. We will add that in next week's lab. And so later on in this lecture, we'll talk about the lab and some of the equations related to the lab. So these combined selection rules are plus or minus 1 for delta V, 0 and plus or minus 1 for J. And these are the transition frequencies. So the transition equations that we're always trying to solve for, here they are. And so you should be able to go in and take this energy equation and derive these different transition frequencies. So here they are. If you took the V to V plus 1 and the J to J minus 1 and did that subtraction and worked through all the algebra, this is what you would get. You would get the vibrational frequency difference minus 2B times J. And so that's what gives you that P branch. So as J goes up, you subtract more and more and more. So that's why the P7 line or the P8 line was so far down frequency from the Q branch, where that would be the Q branch would be the vibrational frequency by itself. And then for that P branch, you subtract 2B for every J value. So when you're starting at J equals 1, then you're only subtracting 2B. But when you get up to 8, you're subtracting 8 times 2B. Now the spacing between those lines then, as you go up in J quantum number, is a unit of 2B. So between all of those rotational lines, you have multiple measurements of the rotational constant. If you put in the other selection rules of V to V plus 1 and J to J plus 1, that's the R branch. And so then you have the vibrational frequency, and you have this sort of offset of 2B moving you over. And then starting at J equals 0, you have units of 2B. So when J equals 0, this is canceled out, but that first R0 line starts 2B up from the vibrational frequency. And then you have J equals 1, you get another unit of 2B. J equals 2, you get another unit. And so on the R branch line, all of those peaks are separated by a spacing of twice the rotational constant. Now let's make life easy. Most of the time when we find the rotational constant, we want to do something with it. We want to find the mass of the isotopic molecule that we have, or maybe we want to find the bond length. And in your lab next week, you're going to solve for the bond length of carbon monoxide. And so don't wear yourself out working on the calculator and typing in all these digits. So this is the rotational constant. And you've got Avogadro's. You've got Planck's constant in there. You have conversion from kilograms to grams. You have angstroms to meters, and they're squared, so it's 10 to the 20. You might even have Avogadro's number in there if you've got things in kilojoules per mole. You have the speed of light. And so you've got all of these different constants, but what's changing? You might have B from your experiment, and you might look up the isotopic masses in grams per mole. Now, if you look them up and they're in AMU, it's numerically equivalent to grams per mole. Okay, so whatever isotopic mass, I see people writing it down, you probably want to write that down. If you look up the isotopic masses in AMU, that's numerically the same as grams per mole. Okay, so on the periodic table, you could say all those masses are also AMU, atomic mass units. Now, and then the bond length. So bond length, mass, and the rotational constant are the only variables in this equation that are going to change. So all that other stuff doesn't change. So just turn it into a new constant. If it doesn't change, it's constant, right? And so go ahead and type all that junk into your calculator, and it comes out to be a really nice number, 16.8576314. And the units are grams per mole, angstrom squared, wave number. And when you divide that by something in grams per mole and angstrom squared, you get wave numbers. So this is note card bait. This is something that you want to have so that you don't have to type in times 10 to the minus 34, times 10 to the 20 and all that. And I want to also teach you this skill. If you're constantly using an equation and you keep typing in the same constants over and over again, make life easy. Just consolidate it into a new constant. And then you're happy. I can type in 16.85 or whatever a lot better than 6.6 times 10 to the negative 34, et cetera, et cetera. Okay. And so if you use that in your homework, you've got homework problems where you're taking HCl and you're coming up with the bond length or the rotational constant and working through those problems, get used to using this, put it on your note card, use it on the test. It makes a lot of sense. Okay. So here's an example. Let's come back to this example though after we've done the Raman spectrum, okay? Because this is using an S branch line. We don't know what that is. I thought I scooted this thing back in the notes. So let's look at the Raman experiment. So again, up at the top we have the levels, and down below we have the lines, the spectral lines. And so again, in alphabetical order, as frequencies increasing to the right, we have O, Q, and S. So just like P, Q, and R, we're in alphabetical order and increasing frequency. The Raman lines, because it's delta J minus 2, that's beyond the P branch, and so they labeled it O, because that's before P. And then because it's delta J plus 2, that's beyond R, and so they labeled it for the next letter S. So it's O, Q, S are the Raman lines. And so looking at this one, this starts in level 3. So J equals 3 here. And up here goes to J equals 5. So this line right here would be the S3 line. And so the vibrational level went from 0 to 1, and the rotational levels went from 3 to 5. And that's a change in plus 2. So you should be able to identify, if I tell you this is an S3 line, what levels are associated with that. You know that 3 is the lower state, and so it's going from 3. You know S is delta J plus 2, so it goes 3 to 5. Then over here we have this big one here is starting, let's see, I was going to try to find the same one. This is the same one here. Okay, so this is 3, and it's coming up to 1 up here. So this is the O3 line. And so that's J equals 3 to 1. And then the Q branch is still the Q branch, no change in J. And that's going to happen only in the perpendicular, in the perpendicular bands. Okay. And so again, the energy level doesn't change, the energy equation doesn't change, but we now have combined selection rules for Raman of 0 and 2. So we have O branch, Q branch, and S branch transition frequencies, and here they are. Now they're a little bit different because they have the incident line of the laser. So where they have the laser line minus the vibrational frequency minus 6B minus 4B times J. And so this 4B is the dependence upon J. So those lines are spaced by 4 units of the rotational constant instead of 2. The same with the O branch. You have the laser line, you have the frequency, so there's a difference there, the Raman effect, and then on top of that you have the rotational effect. And it's subtracted 2B, but then adds back 4B times J. So the O branch, again, is still separated, those O branch lines, by 4 units of the rotational constant. And then the Q branch lines are all going to be sitting right on that vibrational frequency. So in terms of the Raman effect, I have you a couple of slides in here just for your benefit to calculate the absolute frequencies of these. So what wavelength do these show up at? And then in terms of Raman shift, what wave number value they show up at. And so if we're dealing with spectroscopy, Hamlet's always wondering to be or not to be. You've seen Shakespeare. But DW says if it's absorption, it's 2B, but if it's Raman, it's 4B. Okay, so just always remember how those go together. All right, so let's take a Kahoot and see if we've cemented this information into our brain.